Hello everyone, my name is Hugh. I come from University of Luxembourg. Today I present about my work with allocation for UV relay assisted IoT communication network. This is the structure of my presentation today. Firstly, I talk about literature review, what I have done so far, which is motivate for my research problem. Then I propose a solution to solve my optimization problem and simulation results and conclusion. For literature reviews, on literature works they only investigated on uplink or downlink, utilized after-fact communication for the delay-sensitive data exchange. For example, in research number one, they investigated data collection for time-constrained IoT devices on uplink from IoT devices to the UAV only, and they did not consider the latency constraint on the downlink from UAV to ground gateway or UAV to core network. And research number two investigated the latency constraint on the downlink from UAV to ground users. However, in IoT network, the freshness of the aggregated data management of IoT devices when they reach the destination node, destination node, for example, the gateway or the core network, where they need to collect all information for processing, analyze, and predict. Thus, we need to design a new network architecture that efficiently utilizes the limited energy at the IoT devices and guarantee timely delivery of their measurement and status update. This motivates for our works. We propose a novel system model that explores the impact of the battery time-out constraint for the uplink and downlink transmission, utilizing full duplex and half duplex modes. First, this is the first work that usually considered bandwidth, transmit power, trajectory design, storage capacity, and listening constraint for both uplink and downlink in UAV relay assisted IoT network. And in this paper, we aim to maximize the total collected throughput with minimum number of served devices must be satisfied. This is a system model. In this figure, you can see that we have one ground-based station at the center of that area. However, the ground-based station is assumed to be damaged or isolated after a natural disaster, or it is overloaded during peak hour. So we launch a UAV to act as an area-based station to collect data from IoT devices. Then it transmits to the ground gateway. The ground gateway is assumed to have stable connection to control center, for example through optical link with low latency. Due to the UAV can operate in full duplex mode, so we have interference link here. In this figure, we illustrate of two devices for easy to understand about full duplex mode in this work. Device 1, they start transmit data at and start 1 at time slot 2, and the end transmit data at time slot 5. Then device number 2, they start transmit data at time slot number 3, and the ending at time slot number 6. And during time slot 5 to 6, full duplex can happen because the UAVs concurrently collect data from the ground user 2, and at the same time it transmit data of ground user 1 to ground gateway. So full duplex mode can happen here between time slot number 5 and number 6. We introduce about the array. For ease of analysis, we denote one case is the transmission from ground user K to UAV, and 2K is the transmission link from UAV to ground gateway to convey the data of ground user K. And A1K and A2K here represent for the portion of bandwidth that allocate for the uplink to transmit data from device K to UAV, or allocated bandwidth for UAV to transmit the data for user K. P1K, P2K is the allocated transmit power for device K on uplink and for UAV on a downlink to convey data of user K. S1K, 2K here is the channel gain. For the full duplex at the antenna receiver of UAV, we have residual interference due to the transmission of all the user K star different user K at the same time. And we introduce capital R1KN and capital R2KN can be defined like equation 6 and 7. That means the uplink only happen during the time tau 1K and the downlink only happen during the time tau 2K to transmit the data of user K. And tau 1K define the duration between the start time and start K to end time N and K of user K. And tau 2K represent the duration when you can start to transmit data of user K. In this paper, we assume that decode and forwarding is adopted. So the UV need to complete receiving all the data from register K in tau 1K. Then it can transmit to ground K to guarantee the data coding encoding properly. C1K and C2K here represent for the throughput on the uplink and downlink of user K. Next, we introduce a binary variable lambda K. Lambda K equal to 1, that means device K is successfully served and equal to 0 otherwise. So what is meaning of successfully served? This means the data of register K is successfully transmitted to UAV, then successfully received at the ground gateway. Based on above discussion, I propose the optimization problem to maximize the total throughput. Here, R1K time delta T is throughput on the uplink, and delta T time R2K is the throughput on the downlink. And constraint C1, C2 here guarantee the transmission on uplink only happen during N start K to NNK, and the transmission on downlink only happen between N and K to capital N here. Constraint C3 guarantee for the storage capacity of the UAV. Constraint C4 I already mentioned last time. Lambda K is binary variable. C5 means that if lambda K equal to 0, that means user K did not successfully serve. And if lambda K equal to 1, that means the minimum throughput on uplink and downlink should be greater than equal to SK. SK which is the minimum amount of data that user K want to transmit it. And in C6, the total number of successfully served devices should be bigger than a threshold value, lambda threshold. And A1K and A2K is portion of bandwidth allocated for uplink and downlink. In C9, mention the initial location of the UAV and final location of UAV. C10 guarantee the maximum traveling distance of UAV during one time slot, whereas delta D equal to maximum velocity multiplied with duration of one time slot delta T. C11, C12 present about the maximum transmission power of the device and of the UAV. Because our problem is non-convex, because of binary natures of the variable lambda K, and due to the non-convex of all the ray on uplink and downlink. So in order to relax this problem to a convex problem, firstly, we relax lambda from binary variable become a continuous value between 0 and 1 and introduce some slack variable, for example, the distance between the UV at time slot N to device K, and Z2K represent the slack variable of distance between the UAV at time slot N to ground gateway, and T1KN represent the slack variable for the residual interference to the antenna receiver at the UV during time slot N. However, we introduce the continuous value of lambda K but it's not guaranteed that they can convert to UO1. It motivates us to use a penalty function in this paper. And for more detail and about relaxation and all the steps, you should read my paper. So at the end, we can obtain the converge problem like this, which you can solve by standard method like Seagate. And the solution we summarize as follows. Firstly, we employ the inner approximation framework to tackle the non-converged relax problem. We perform some relax method, which is represented detail in our work. You can read for more detail. And secondly, we relax the binary variable into continuous value, and the objective is then analyzed by entropy-based penalty function. And the proposed solution guarantees the conversion to at least one local optimum solution. And this is about the simulation result. In the simulation result, firstly, we investigate the achieved throughput versus the network size. And we can see that with the larger network size is, the lower throughput can be achieved. However, in the first case, A here, when the bandwidth is large enough, the multiplex doesn't change. The performance of multiplex is still very good. However, when the bandwidth is lower, the performance of multiplex also decreases. However, the multiplex method can obtain better performance compared to other methods like benchmark, multiplex, benchmark, half-duplex, or half-duplex. And the benchmark multiplex and benchmark half-duplex we implemented similar to multiplex and half-duplex, but with equal bandwidth allocated to each user. In next figure, we investigate the throughput versus the cache size. When the cache size of the UV increased, the performance also improved. And especially when the flying time is large enough, the performance of multiplex and half-duplex is the same here. So in this scenario, we should upgrade in the half-duplex mode for a simpler implementation in comparison to that of multiplex. And the conclusion of this paper, we have some major contribution. We firstly investigate the trajectory design for multiplex, half-duplex, both the uplink and downlink in UAV-assisted IoT network under latency constraint. And the total achieved throughput will maximize by generally optimizing allocated bandwidth with power trajectory, while we need to comply with delay sensitive data collection and limited storage capacity, which is a non-trivial problem. Thank you very much for your vision.